Good morning, good afternoon, and good evening, based on the zone you are watching this presentation. I want to welcome everyone once again to WP3 Scientific Achievements presentation. And my name is Emmanuel Lamon, and from IT, a co-leader of Work Package 3. I'm presenting on behalf of the team, of the Work Package 3 team. The organizational mission of WP3 in the RTBfoods framework. As you can see on this slide, 5 researchers assume the coordination of the work package, and 8 institutes are engaged in WP3 works. This institute originated from seven countries, and these are Uganda, Nigeria, Colombia, Peru, and Guadeloupe, Ghana, and France. What is the main mission and the role in RTBfoods framework, that is WP3? Our mission is WP3 develop high-throughput phenotyping protocols that can be applied in national and international breeding programs. And our main role is in relation with WP2. We try to, in cooperation with them, during the sampling, codification, analysis, and WP4 is involved in sampling, codification, and predictions. What are our contributions to the output of RTBfoods projects? Our contribution to the following output. The first one is screening capacity for quality traits developed, and then the second one is high throughput phenotyping or medium throughput phenotyping protocols developed for quality trait screening, and also RTB spectral databases and calibration for quality traits. In this period 3, we really affected by the COVID-19, and mainly on majority of trainings were cancelled, especially the trainings that involved the field trainings, especially, for example, that of NRCRI. We plan to be there with them to work them on the field, but we couldn't travel because of the COVID. Another effect of COVID is scheduled harvests were impossible, or if they were possible, they were very late in the year. And this particular effect caused result in delays in NIS and also in chemistry analysis by WP2. Also, some databases and arbitrariness were not done, and then we plan all these delayed activities. We put it in period 4, and we hope that we are going to do that in period 4 as the COVID effect is subsiding. In period 3, under SOPs, we developed 14 SOPs, and the breakdown is NACRI 3 SOPs, IIT 3, CIRAC 5, NRCRI 2, and CIAT 1. The procedure for the SOPs, we have a team which is being headed by Karima for the editing, and then the submission by the partners, and then the reviewing is being done by the coordination team, and correction and final validation are being done by WP3 leaders. So these SOPs cover different product profile, that is different forms. We have the intact fresh roots and tubers, we have the ground fresh, we have the ground dried, and then the semi-processed products. So the MTP and HP techniques were used for development of this SOP, and this starch grain size measurement by CCD camera, and the color oxidation by using the colorimeter. Diverse instruments were used, benchtop, portable spectrometers, hyperspectral camera, and CCD camera. Data management and ontology. We generated a lot of data from period 1 down to the period 3. So what we did in period 3 is we changed the template. We developed a new template in order to meet the BTS format. We developed a template to unify the spectral databases format. All spectral databases submitted and they were validated using the template by our partners. And we have over 4,000 niche spectra uploaded in Prebase, about 1,000 spectra in cassava base, almost 3,000 spectra in sweet potato base, and about 249 spectra in yam base. What are the challenges we faced in data management ontology? The first one is we find it difficult a little bit to link spectra to the trials metadata, and also difficulty to put spectral data in DTI format. We tried, and then we were able to overcome the challenges, but we hope in period 4 we will perfect this. We will perfect this solution to these challenges. What are the next steps for data ontology? We plan that each partners to appoint a data manager. Some, they have data manager now, but we are believing that PMU will coordinate this, all the data managers to have a training and then to have a expectation that we want from them. Each data manager will manage the uploadings of all spectral data into the Prebase, so together with the WP3 coordination. Databases and calibrations during the work package 3 regarding the output 1.53, 1.54 related to RTB databases and calibration. The WP3 strategy was to develop a specific form shared with different teams. So what we did is we developed a standardized form for collection of spectra and non-metadata, as we have done to develop a template, which I mentioned before. Then we scanning according to SOPs and sample codification done at team levels. So the spectral acquisition for the development of prediction models. Cassava, we have around 7,000, yam 200, and banana 377, sweet potato 609. So different forms, we have fresh intact, fresh ground, and dry flour. So the products include the meal and unmade garri, wet fufu, and sweet potato. The spectral databases for good and poor genotypes, we collected some data bases for that, and also data set dedicated to instrument standardization. Databases calibration continue. The proof of concept and calibrations. What are those things that we achieve under that? 20 calibration developed and improved. The main constituents calibrated refer to major traits such as the dry matter, proteins, starch, sugars, and micronutrients. For example, carotenoids. The physical and functional properties we explored include color, texture, and functional parameters such as swelling power, dispersibility, and solubility. The calibration performances are unequal, yes, in terms of the specificity and selectivity and accuracy. And we propose that it needs a major improvement, which we are going to do in period 4. The hyperspectral imaging potential was tested for characterization of boiled yam, like cooking degree of time, and then we have POCs that were done on good and poor genotype discrimination, which mainly concerns cassava and yam. The good poor philosophy, we want to just present 2 or 3 slides on that. We plan on in WP3 to look at a way where we can be able to solve some traits that are not easily predictable, and in order to help the breeders to have a good instrument to to screen their breeding materials as quick as possible. So the good and poor approach is a shortcut between WP1 and WP3. That is, the data generated from WP1 can be used to link with the spectra in order to be able to classify, yes, these materials based on the responses, and it can be a binary responses, so that we can be able to develop needs and then use it to classify these the materials. Yeah, is capture biophysical drivers or preferences is necessary, but they are complex. We all know that, and so that good and pure HPP method can complement classical approach. So, yeah, what is the methodology of the good and poor in comparison with the compositional traits? The prediction of functional traits or overall quality by NACE, it relies on complex mechanisms involving many compounds, potentially linked by nonlinear relationship, yeah, threshold or composition effect. Therefore, classical prediction such as PLS is a little bit difficult, so it seems unsuitable for some functional traits. And so also it often rely on tedious and less reliable reference method, so leading to small and noisy data sets, e.g. the cassava cooking time or yam pandability, for instance. They are quite hard to quantify and take time to do. Good and poor prediction belong to classification problem rather than regression. So most of the time, classes are unbalanced. For instance, 100 slow cooking genotype, 40 fast cooking. This implicitly led to unbalanced weight for each class. So for all these reasons, we choose to bring some innovative tools to address such challenges. Convolutional neutral network is one of the solutions we brought, and also the feature augmentations in order for us to generate, not to generate more noise, and then the feature and data augmentation as well. So these are just the proposed solutions, improvements we brought into the good poor methodology using deep learning machine. If we need more details, and then we can refer to the webinar that we deliver, Dennis Connect delivered some times ago. You can refer to that, so to get more information on the good and bad methodology. So good poor databases, we try to view the database, good poor databases. For some traits, as been mentioned, that some traits were being developed as classification for yam modability, and then for cooking time, and then the yam good or poor genotypes. So 81 samples for yam modability. The trait is modability after mechanical pounding, which the response is yes or no. The second data set is to classify the fast and slow cooking root of cassava. And then the third data set is for MITA, which is provided 200 yam samples with a binary classification of genotypes relying on suitability for pounded yam. So the preliminary results is very encouraging. We used open source software, and despite the small size of the available data set, so first result demonstrated good accuracy of the method here. And indeed, accuracy was always higher than 80%. So as we can see, 0.8 for yam moldability, 0.93 for yam good and poor, 0.860 for cooking time. So the preliminary results open up a very promising prospect for breeding program. Should this result be confirmed, the objective will be that we need to calibrate a model by product profile based on the rawest possible material, e.g. grew fresh yam and the fresh fruit, cassava and sweet potato. During this period, we have 3 publications under WP3. 1 review paper on NIST application in cassava yam, which is published in IGFT, it's under the special issue, and one paper on prediction performances of near infrared for quality trait of fresh yam. And then the other one is on predicting quality texture and chemical content of yam tuber using near infrared spectroscopy. This paper has been accepted and is going to be getting DOI very soon. So the highlight from the papers, different high throughput procedures for characterization of cassava and yam germplasm, they were identified. And we can also see that deep learning classification algorithm allow to produce a rapid prediction of pounded yam composition and texture. And the NIST could be used also to produce a rapid prediction of most of quality traits. The calibration models performance statistics showed a good R-square prediction for dry matter, starch, protein content of yam samples for blended method. Successful analysis of fresh tuber crops with NIST could lead to elimination of the tedious sampling preparation process. So that's our ultimate in this project, that we want to make sure that breeder can have a models that can work on the fresh materials as much as they can. Yes, in conclusion, all the teams run NIST as routine. That is what we observe, that all partners, they run NIST as a routine. They use different spectrometer, although the spectrometer used are different. Some are used bent top, some are used handheld. So for all raw root and tubers, we've worked on all raw roots and tubers in different forms, and also the feasibility of NIST for processed root and tubers were also exploited. That is especially intermediate product, gari, fufu, and matoke. 14 SOPs developed and validated, and also 20 calibration and the proof of concepts were developed as well. Four MTP techniques investigated, which include MRS, colorimetry, image processing, and hyperspectral imaging. Poor and good genotype approach were validated. 3 articles of main results published. What about our perspective for period 4? The first one is we want to consolidate the developed calibrations we have in period 2 and 3, and then we need to develop more models to qualify genotype as good and poor, and also to harmonize the SOPs, especially the SOPs on intertruth using portable spectrometer. So we still want to work on HSI more, image processing, and the mid-infrared spectroscopy for specific properties. We want to ensure that genotype from WP4 analyzing priority and reinforce coordination with the WP2 and also WP4. Want to just mention some things on perspective for good and poor, because we see that's a good approach. So we want to give more time to it, this in period 4, to be able to perfect and extend it to all other product profiles. So the first thing we will do there is to evaluate the robustness of the predictions model, and then also to to tackle other RTB products based on historical database or new trial. That is, you may use historical data sets or we use a new trials. But for those that we have worked on before in period 3, we want to extend to a new trials in order to increase the robustness of the predictions models. Yes, apply the same technology to study other 1D signals, that is to extend it to other parameters, and then to improve the interoperability with the VAE and the GAN. Improving performances using model assembling like e.g. stacking. So these are just the perspective for good or poor POC which we plan for. We want to acknowledge all the institutes that are working under Work Package 3. They are the following: NRCRI team, IITA team, NACRI team, CIAT teams, ZIP team, INRAD team, NAR team, CIRAT team, all partners from the Work Package 2, Work Package 4, and Work Package 5. We want to acknowledge PMU team for their supports, especially in helping us to organize the virtual meetings from time to time during the period under reporting. The advisory committee also, we need to acknowledge you for your series of advice you are giving unto us, yes, in our Work Package 3. And finally, we thank our sponsor, the Melinda and Bill Gates Foundation, for their financial support. Thank you.